So, success criteria. I think I'm competing with you guys. I don't think there's a need for laptops to be open. You may disagree. I can identify and use the perfect square rule to expand a product of binomials. And secondly, I can identify and use the difference of two square rules to expand a product of binomials. So by product, I simply mean two things, or two or more, but in this case, it's two things multiplied together. And remember that binomial simply means that we've got two terms added together. So A plus B times C plus D would be the product of two binomials. Hang on a sec. Okay, so what I'm going to do is I'm going to present the rule itself, which you should be familiar with from grade 9 maths core. I'm then going to present you with a simple example and then have a look at some more complex ones. I won't actually solve every single complex one, but we'll at least have a look at them, and then maybe I'll expand upon one or two of them so you can see how they go. So that's the nature of how we're doing it. So I'll just zoom out so you can see everything there. So the perfect square rule is like this. A plus B. So two terms added together, and the whole thing is squared, is equal to square that first term plus 2 times A times B. So multiply the two terms together and double it, plus square the last term, or the second term. So it's A squared plus 2AB plus B squared. If instead you have two terms subtracted from each other and the whole thing is squared, then it's the similar pattern like so. We square the first one and we actually square the last one. It's the middle term that's different. Instead of adding, we take away. So can you see that the sign in the middle repeats itself for the middle term? Okay, so sometimes you might see the rule written like this: A plus or minus B all squared is equal to A squared plus or minus 2AB plus B squared. And effectively, that's the rule. Now, I'm going to show you how to utilize that rule, but I just want to check to make sure everyone's okay with that before I move on. Can you see what I've done there with the plus or minus? So as long as you follow through with the right sign in the middle, you are good to go. And have you noticed that regardless of whether you're adding A and B or subtracting A and B, B squared is always positive? Okay, so it's just that middle term that's different. Let's have a look at an example. So this example here is 3 minus x all squared. Now, I'm just going to put some explanatory notes in blue. I wouldn't necessarily ask you to write these all the time unless you think it would be useful. So let's identify A. So A is the first thing, so that would be 3. B is the second thing, the second term, and that would be x. So in our formula, we are simply going to utilize this rule here, but substitute instead of A, have 3, and substitute instead of B, have x. And so our next line would is 3 squared minus 2 times A times B. Can you see how I wrote 3 and x as I said A and B? So 3 squared, or A squared, minus 2 times A times B, plus B squared. In this case, B is x. And then the last line is just to simplify. So collect like terms, multiply numbers together, all that kind of stuff. So 3 squared is 9. 2 times 3 times x. Now, note that there's no distributive law there. It's just 3 things multiplied together. So it's not 2 times 3 and 2 times x, because that only works if you've got an addition. But these are all multiplied, so it's simply a matter of multiplying the number bits together. 2 3s are 6, and then putting the variables after it. 6 times x is 6x. So it's 9 minus 6x plus x squared. Okay, does anyone have any questions so far? Okay, don't write this next bit down yet. 9 minus 6x plus x squared is then equal to 3x plus x squared. What's wrong, Tom? Yep, I'll come back to that in just a sec. Just focusing on this line here. Everyone okay with 9 minus 6x plus x squared is 3x plus x squared? Just nod if you're okay. I'm not seeing enough nods around the room. Thomas, what's the story? Yep. Right, lovely. They're not like terms. Yep, that's exactly right. Thanks, Jack. So they're not like terms. So you can't actually do that line in red. So that is as simple as you can get. 9 minus 6x plus x squared. Now, technically, you could then rearrange this to have the x squareds at the front, but it doesn't matter so much when you're doing a perfect square like that. I'll be more than happy with 9 minus 6x plus x squared as being the final answer. Okay, any questions about that? I'm going to come back to what you asked though, Tom. Okay, let's just focus on that to make sure we're okay. The rule is square one term, square the last term, and in the middle, it's twice a times b. So the 2 over here comes from the 2 in the rule. It's just always, always, always. And then the 3 comes from the fact that it's 2ab, and the 3 is like the a. And the x, or here with the a minus b, and the x takes the place of the b in the 2ab. So it's 2, because that's what the rule says, a, because in our example, a is 3, x, because in our example, b is x. So it just becomes 2. Now, whilst you're trying a problem out, I'm going to, after you've tried a problem out, I'm going to explain why it's 2ab, but you don't need to know why it's 2ab. You just need to be able to use the rule.
By writing a squared plus 2ab plus b squared, you imply that it's a times b.
Can you say that again, Blair? Because I'm not quite sure where the confusion lies at the moment.
So, like, say you had 3 take x squared, it would end up being, say, x squared plus. It's like you're adding these two together. You're not times them together. You're adding them together.
Yeah.
Yeah, but by writing it as like 2ab, it's sort of confusing.
But when you add them together, you're basically doubling it. You're doubling two negatives. Yeah. But I'm going to show that in a minute. So, sorry, voices off, please. And waterfall. Thank you. What Blair was saying in a nutshell was what Blair showed me on his piece of paper was that he did a box method expansion, and he wasn't quite sure where this 2 comes from as a result of the box method expansion. So once I've gone through some examples with you, I'm going to actually show you why the perfect square expansion always works. Like I said, it's not essential that you know that, but I know for some of you, knowing why it works is key to you remembering it and using it. But honestly, the main thing is that you just simply need to be able to use it. Now, being able to use it means being able to readily recognize when an expansion can be done using the perfect square rule. That's the key to this whole experience, right? So it's one of those things where if you can recognize that it is a perfect square problem, then you can use the perfect square problem. We okay?
Yeah.
You sure? Yeah. We can use the perfect square rule to shortcut our maths because perfect squares and difference of 2 squares are so common. Okay? So instead of having to use the box method or the chicken beak method in order to expand a problem, we are able to use the rule and therefore miss quite a few steps. So that's why we're doing it. Now, what I know to be true is that for many of you, not all of you, but for many of you, you're going to have a look at these sorts of problems and you're going to say, but I can do the box method. I just do it and it's fine. I can do it. It's easy. So why would I have to do this instead of using the box method? And I want to give you a meaningful answer rather than just do it, because it's going to be on a test. So if you don't do it on the test, you're just going to fail. So rather, I'll give you a more meaningful sort of reason why. These rules are effectively shortcuts. And I guess the closest analogy I can think of is maybe if you're doing some sort of extracurricular activity, like a sport, for example, and you know that sometimes in those sorts of activities, there are better ways of doing stuff than others. You can improve your technique, or you can improve the number of techniques you've got in order to complete something much more successfully. So what happens typically is that you've got your old way of doing it, and then someone says, you know what, if you just change the way you're moving in the water, or if you just do it in this way instead, then you'll actually become a better performer in whatever you're doing. And then you think initially, because your coach has told you to do so, you start doing it, but it's painful at the start. It takes longer because you're used to doing it the old way, where you have automaticity. You can just do it without thinking, really. It just happens for you. But as you train, the new technique becomes more and more readily accessible to you. It becomes more automatic until it is just as automatic as the old technique is. But because the new technique is better, you are suddenly performing better overall. Now, this is what these techniques do for you mathematically. By training yourself to use perfect square, by training yourself, what you're doing is longer term, you're then developing these techniques. You're developing these techniques so that you can tackle harder problems more easily and more readily. So I don't stand here and say to you that right now the perfect square method and later on the difference of two squares method is something which is just everyone picks up straight away and is fine with. But I'm saying it is worth persevering with, so that when you do more complex stuff, these sorts of tools will be really close at hand for you. Okay, so that's perfect square in a nutshell, and I'd like you to practice them in a second, but I'm just going to push through the theory a little bit. And in this fourth slide where it says, when is an expansion a perfect square, I want to just put down some examples without going to a full solution as to expansions that might not quite look like a perfect square, but in fact are. Because that's when it becomes powerful, when you can look at an expansion and ask yourself, is it a perfect square? Okay, so the first one's a pretty obvious one, I think, but maybe it's not, which is why I'm going to write it down. X plus y times x plus y is a perfect square, because I'm effectively multiplying something, in this case x plus y, by itself. So x plus y is equal to x plus y all squared, and therefore I can use the perfect square rule to solve that problem, and should. That's the most straightforward one. The rest of them aren't as straightforward. This one, 2x plus 6 times x plus 3. Now, on its own there, it definitely does not look like it's a perfect square, or that a perfect square expansion could be used. But you definitely can. Have a look at that first binomial there, 2x plus 6. Have you noticed something about that? Raise your hand if you wanted to suggest, because otherwise we're not going to have good conversations in class. Will? In other words, you recognize that there is a common, thank you, Will, common factor. Okay, so as Will said, there's a common factor of 2, and then he went on to say that there's 2 outside of. So just to explain what we're talking about here, if I have a common factor of 2 here, 2 goes into both of these numbers, then I can draw that 2 outside the bracket and say 2 times what equals 2x, x, 2 times what equals 6, positive 3. So there's my positive 3. So now I've got 2 outside of x plus 3 times x plus 3, which equals 2 outside of x plus 3 all squared. And then you can use the perfect square rule. So when you're looking at an expansion, maybe see if there are common factors first. Will that, if I take out the common factor, will that in fact give me a perfect square? I'm going to start writing small now so I can get a few more examples in. Notice that I'm not actually solving any of these. I'm just showing you how to put it into perfect square model. Next one is, yeah, this one here. Is that too small down the back? That one there? Okay, cool, because I want to squish them in if I can. So initially, it definitely doesn't look like a perfect square because I've got negative x minus 3 and I've got x plus 3. But it's so close that I feel like as if maybe we should have a look at it. I'm having a bit of chatter over the other side of the room. Please take your chatter outside. I'd rather you miss out than a bunch of people miss out because I'm being put off and people are being distracted by your chatter. You make a choice. I don't care, but just go if you're going to talk. So negative x minus 3 times x plus 3. Now, to be honest, that's no harder than the one above it. It's just that it's got more unusual common factor. So I might even zoom up actually because you don't need to see all slides and that way you can definitely see everything going on. Okay, so negative x minus 3, x plus 3, that first binomial has a common factor of negative 1. So if I take the negative 1 outside the bracket, which typically is just the negative sign itself, then negative 1 times x is negative x, and negative 1 times positive 3 would give me negative 3. Okay, so taking a negative outside the bracket, as we have done in the past, has just changed the signs of the stuff inside. So we've got negative x plus 3 all squared. Okay, so once we can reformat our question into something that looks like a perfect square, it's then solvable. Another example is something, this isn't too bad, but something like this. 2x squared plus 1 times 2x squared plus 1. That is definitely in the perfect square format. It's just that the terms are quite, well, the first one at least is a little bit more complicated. Okay, so first of all, it's 2x squared plus 1 all squared. And all we do is we make sure that we understand that A is 2x squared and B is equal to 1, but it still fits the pattern. It's just that when we square it, we have to square all of 2x squared. That's all. Which can be complicated because you've got to use your index laws and stuff, but it's not impossible. And the last one, I think, from memory, yep, is this one here. X plus y plus z all squared. Now, looking at that, I need to make it sure that you understand very clearly that as it stands right there, it does not fit the pattern of a perfect square. Sure, we have some things added together and the whole thing is squared, but it's not 2 things, it's 3. And a lot of people go, yeah, but it's kind of the same, so the rule applies. No, maths isn't like a kind of sport. It's a very specific way of writing, okay? So if it doesn't fit the pattern exactly, then we cannot use the pattern. In this case, I can sort of cheat a little bit. And the way I cheat is like this. Let A equal x plus y. This is called a substitution step. by letting a equal x plus y, I can then rewrite my equation. Oh, come on. I can rewrite my equation as a plus, a plus z. Oh, it's gone purple. That's interesting. All squared. Okay. So by letting a equal x plus y, I now have a plus z all squared. And then I can, now it is in the format of a perfect square. Okay. Now, what happens then is it gets a little bit tricky from that point on. So you'll use the perfect square rule and you will get you'll get something with an a in it, but then you need to substitute x plus y back in for a and solve further. So it's not that hard. It's just there's a lot more steps, and when there's a lot more steps, there's a lot more room for error and so on. So they're just some examples of expansions that might not look like a perfect square, but in fact are, with a little bit of tweaking. Alrighty. So what I want you to do now for the yes, Tom. No, you can still expand it using perfect square by letting a equal x plus y, expanding a plus z all squared to something, and then substituting back x plus y. I'm not solving it right now for you, although I'm happy to do so at some stage. But just note that after you've done that, you'll get some x plus y squares that then need to be expanded further. So it's definitely doable, but it's just lots more steps. So it's not as simple as just saying it's just the same as x plus y plus z all squared. Okay, so what I'm going to do now, I'm going to pause the recording and I'm going to give you a problem, just a nice simple one to try. But if you want to try and do one of, not the top one, but one of these ones instead and see it through to conclusion, you're welcome to. After we've done that, I'm going to ask if anyone wants me to go through one of these problems, one of these harder ones, just so you can see how it's done. Okay, so I'll pause the recording and write a problem up on the board, but I'm only going to give you like 2 or 3 minutes to do it. Okay. So I've been asked to show 2x squared. What was it? Plus 1, wasn't it? So we have 2x squared plus 1 times 2x squared plus 1. And I guess the first thing to note is that can simply be written as 2x squared plus 1 all squared. And now we follow the same rule. So we say square the first term. The first term is hard, but as long as we keep our wits about us, it's okay. So the first term is 2x squared. So just watch what I do with this one. I'm going to write 2x squared down, and then I'm going to square it. Now, you have a look at that. That looks ambiguous. It looks confusing. Am I squaring the 2? Am I squaring x squared? Am I squaring 2x squared? Now, we need to square the whole of that first term, but leaving it like that is just a little bit shaky. So in that case, I put brackets around it to show that it's the whole term that I'm squaring. So we've got 2x squared all squared plus, because it's an addition, 2 times the first term, 2x squared, times the second term, plus the square of the second term. Now, I understand from my other class that you guys in core have looked at index laws. So because I need to get through lots of more material, I'm going to do this next bit a little bit fast, and I hope you can keep up. Because I've squared this complicated term here, I effectively have to square both things inside, because it's not an addition, it's a times. So I go 2 squared is equal to 4. And then x squared squared, when you have a power that you raise to another power, do you remember you multiply those powers together? So 2 2s are 4, so it's 4x to the power of 4. In the middle, again, I just pick on the numbers first. 2 times 2 times 1 is 4. And that leaves me with x squared, which is just by itself. So it's 4 times x squared, or 4x squared. And 1 squared is 1. So that's the full expansion for 2x squared plus 1. It's not that bad. What makes it horrible is that 2x squared needing to be squared. Tom?
I thought you said you could collect like terms by doing 2 times 2x squared.
Okay, so expansions, collecting like terms, always think of them as relating to pluses and minuses. When I collect like terms, it's like 3x and another 4x and another 7x minus another 12x. That's collecting like terms. What I'm doing here is multiplication, and things can be multiplied together, no dramas. So x times y is xy. Sorry, Josh. Okay, A times B is AB. You can multiply things together, but you can't add or subtract things together that aren't like. Does that clarify that? Okay, thanks for that question. Anything else? Right, so looking at time constraints, I might, I'll still go through it, but I'm going to do it really super fast because you don't need to know it. It's really just for completeness. So I'm not going to take any questions from this. So A plus B all squared means A plus B times A plus B. A times A is A squared. B times B is B squared. So that's those two things. Now, in the bottom left-hand corner, A times B is AB, and the top right-hand corner is B times A. And B times A is the same as A times B. So we've got an AB there. So across the diagonals there, I've got 2AB. So there's my A squared, there's my B squared, and there's my 2AB. With A minus B all squared, I have A minus B and A minus B. I get A squared there. Minus B times minus B. The negative times negative makes it positive, which is why we have positive B squared. And then if I have a look at the other diagonals, I have A times negative B is negative AB because it's a positive times a negative. And negative B times A is negative AB. And what I'm doing again is I'm collecting two terms that are the same sign. So I've got minus AB minus another AB. So that gives us minus 2AB. So you can see that with either expansion, I end up with 2 of the ABs. And the negative just comes from this idea here. So that's all I'm going to say on it. Dots is not too bad. What makes dots a critical thing for dots, I guess, is that with dots, you only end up with 2 terms after you've expanded it, not 3. So I'm going to go through this. The rule is this. If I have A minus B, so 2 terms that are taken away, and then I have A plus B, the same 2 terms, but they're added together, I get A squared minus B squared after expanding. Now, I just want to write this down as well, just so you've got it. It doesn't matter the order of the 2 binomials. So it can be A minus B times A plus B, or it can be A plus B times A minus B. Both of those give us the expansion A squared minus B squared. Notice that order of inside the brackets is important. So it has to be A minus B followed by A plus B. It can't be B minus A times A plus B. Okay, so the order is important in the subtraction. Any questions about that? Let's see an example then. I'll keep that zoomed out now. So we've got 3 minus 4x times 3 plus 4x, sorry. So that is equal to, so it's like 3 takes the place of A and 4x takes the place of B. We can see it fits the pattern because I've got a 3 here and a 3 here, and I've got a 4x here and the same here. They're taken away here and they're added together here. So this does work. So we square the first term. So that's 3 squared minus the square of the second term. Now, again, like I showed you with that last example, if I went 4x squared like that, it looks like 4x squared, but we're not just squaring the x, we have to square the whole of the term, and so I put brackets around it like so. So it's 3 squared minus, in brackets, 4x all squared. Okay? So that's the use of dots. I've got one more line to go, but that's using the dots rule there. So dots, difference of two squares. You can see that the expansion is a square minus another square, and minus means difference. That's the other word we can use for it. It's a difference of. So that's where dots comes from, difference of two squares. So the last line, 3 squared is equal to 9. And 4x squared, we square each thing inside. 4 squared is 16, and x squared is x squared. So it's 9 minus 16x squared, and that's all we can do. We can't take 16 away from 9. Any questions? Alrighty, let's have a look at some examples. First one I think I'll try with you is this one. So we'll just zoom up so you can, oh no, I'll leave it zoomed out while people are still writing a bit. So the first one is like this, 3 minus 4x times 4x plus 3. So that is still a dots problem because the sum, the addition bit, the second binomial, that can be reordered. You can't reorder 3 minus 4x because, you know, like 10 take away 5 is not the same as 5 take away 10, right? So, but I can reorder a sum because 10 plus 5 is the same as 5 plus 10. So that equals 3 minus 4x, 3 plus 4x. So that's okay. It's in the right format. Just like I did last time, I'm not intending on solving all of these. Questions? I'm happy with murmuring as long as the murmuring is because you've got questions you need me to answer. Okay, a few more then. 6 plus 8y. Times 3 minus 4y. That's really similar to the other one we did, isn't the first one we did with the perfect squares. There is a common factor in 6 and 8. So I'll take out the common factor of 2. And I'm left with 3 plus 4y, sorry, times 3 minus 4y. I'm just going to zoom up on that now. I think I've given people enough of a chance to write that down. Is that okay? So common factor again. So again, when I find when I've got an expansion to do, my number one job, I suppose, is to see whether it will fit another rule or not. Okay, so if I can use perfect square or dots, then that's what I'm going to use as my first tool. It's only when it fails, when I fail to be able to use it, that I move to the box method or chicken beak method. That's really important. And I know it seems harder at the moment to look for these rules, but again, that's because you just need to practice them until it's not so bad. Now, this one here is really common. Just want to make sure I'm getting it right here. Four n minus 3 times 3 plus 4n. It looks like it should fit. There's not much that's wrong there. We've got a 4n term, we've got a 3 term, we've got a subtraction and we've got a plus, but we've got this issue where that first term there, it's around the wrong way. This can be changed. What we do is we take out, yes, Thomas? To 4n plus 3. Yeah, that's what I did before. Have I just chosen a dodgy example? Yeah, you can. I've chosen a bad example. No, I mean, it just happens, right? I mean, that's okay. We're all human. I've chosen a bad example, but what I'm about to show you is kind of relevant for specific examples where you can't just swap stuff. So I'm going to follow through with what I wanted to say, only because for me to think on the top of my head of an example that would work properly, it's just going to be a bit of a derail for me. So I apologize for that. Yeah, but you're absolutely right. And good on you, Thomas, because that's exactly what you should do. Just swap 4n and 3 over, and then you're good to go. But what I'm going to do is just persevere with what I wanted to show you. And that is, if you've got 4n minus 3 and you need it to be 3 minus 4n, if you take out a common factor of -1, you get what you're looking for. So negative, and then have a look. We would have -1 times -4n will give me positive 4n, and then -1 times positive 3 will give me -3. So it becomes -4n plus 3, and then 3 plus 4n. And then I can rewrite that particular first binomial as 3 minus 4n, and then 3 plus 4n. And then you're good to go. So again, sorry, the example's not great, but that technique of taking out a negative just so you can swap the signs of the stuff inside the bracket is a very common technique in algebraic manipulation. So it's worth remembering that, even though it's not the best way to solve that particular problem. Yeah, I could have done, but I'll leave it as it is there for the time being. Okay, so does anyone have any questions about that? I'm sorry about being a bit confusing there, but that idea of taking out the negative is really important. And typically, after you sort of master the skill of taking out a negative, you can see that this line here is not really useful. It's just this bit here. So when you take out a negative, you swap these operations around. So a negative outside the bracket means you're going 3 take 4n instead of 4n take 3. And the last one I wanted to show you was a bit of a similar sort of thing to the last one and the other one, which is if I have, I want to make sure I get it right, 5 plus a minus b times 5 minus a plus b. Now, on the surface, it looks like that cannot be expanded using dots. Because, to be fair, we certainly don't have all pluses and all subtractions, but more importantly, we have 3 terms there. We have 5 and an a and a b and a 5 and an a and a b. So 3 terms for each binomial. So it's not a binomial, it's a trinomial times a trinomial. So it doesn't work as it stands. But I want to show you a couple of tricks there to make it work for us. The first thing I'll do is I will just go 5 plus, and it's the a minus b I'm going to keep together. Okay, because you can see it kind of nearly works with the 5 plus and the 5 minus. So 5 plus a minus b, and then I'm going to take the same approach here, 5 minus, because when I take a minus outside the bracket, remember everything inside changes. So the a stays where it is because it's minus a, but minus 1 times b is minus b. So I end up with 5 plus a minus b times 5 times 5 minus a minus b. So if I then go something like this, let x equal a minus b, then I get 5 plus x times 5 minus x, which is a difference of 2 squares pattern exactly. Okay, so what you would do then is you would use dots, so you have 5 squared minus x squared, and then with the x, you would then change that back to a minus b and expand it using perfect square rules. But again, I'm trying to show you that there's a whole bunch of different problems without solving them because I don't want to overcomplicate it at this stage. Like I'm just saying there are lots of possibilities. Yeah. No. So by taking it's the act of using a subtraction with brackets around it that has allowed me to remodel it as an a minus b. But if that was 5 plus a minus b and 5 take away brackets a plus b, they wouldn't be the same thing, would they? So you can only do it if they're the same thing. An a minus b here and an a minus b there means they're the same thing. Any questions about that? Okay, so with the 5 minutes left, I'm going to ask you to have a go at either doing one of those ones on slide 8, or if you just want to see whether you can do a more straightforward one, I'll write it up here. And next lesson, I'm going to give you plenty of practice time on perfect squares and difference of two squares, maybe about half an hour's worth of practice. So either one of these ones, if you want to try it. Otherwise, you can try 7 minus x, 7 plus x. You can try that.
Which is there.